Thank you. So my name is Matthias, and I'm a PhD student at ETH in Zurich, Switzerland. And I focus on bone imaging and computational modeling as part of the FIDELIO project on diabetes in bone. And so today, I want to talk about time-lapse high-resolution peripheral quantitative computed tomography, or short HR-pQCT, and bone mechanoregulation. And yeah, so now. So as many of you are probably familiar, diabetes mellitus is a widespread metabolic disorder, and it's affecting 1 in 11 adults worldwide, and even 1 in 4 in the age group older than 65, and numbers are steadily increasing. So there's 2 types of diabetes: type 1 diabetes, where patients have no pancreatic insulin production. These patients are usually younger patients debuting during adolescence, so age 15 onwards. And type 1 diabetes makes up 5 to 10% of the cases, and these patients show increased fracture risks of about 6-fold. Then type 2 diabetes makes up around 90% of the cases, and here patients develop an insulin resistance over their lifetime, and these patients are therefore older, around 40 years of age typically, and they have a 2.5-fold increase in fracture risk. Overall, both groups show increased fracture risk and poor healing outcomes, which is why we're looking to improve their bone health. To assess fracture risk, despite the traditional methods of using DEXA and T-scores, high-resolution peripheral computed tomography, or HR-pQCT, can be used to measure the bone microstructure and alterations, which is really important for bone strength. And here on this slide, you can see on the left a study that looked at bone microstructure in control and hip fracture patients. And you can see really the differences where even though these scans are not scanned at the hip, but the distal radius and tibia, the bone microstructure is really impaired due to this metabolic impact of the osteoporosis. And you can see some distinct features, for example, these large holes forming, or these like trabecally thinning, which is different from the control subjects. And on the right side, you can see a meta-analysis that has actually looked at several studies that investigated bone microstructure and linked it to the fracture risk. And this study showed that a lot of these measurements that can be done with HR-pQCT are related to fracture risk. Then I want to highlight maybe, besides reduced BMD, this increased cortical porosity, or this increased trabecular separation, which is highly increased in these fracture subjects. And of course, HR-pQCT can also be used to measure bone microstructure in diabetic patients, and this can be done at the distal radius or the distal tibia. And we've performed a meta-analysis looking at the distinct microstructure alterations in these patients. And what we found is really interesting, that these types show really different bone phenotypes. So in type 1 diabetes, we find a kind of like increase in this trabecular inhomogeneity, which is what I pointed out earlier, these large void spaces or holes forming in the bone matrix, where there's sometimes really large spacing between trabeculae and sometimes smaller spacing. So it's very inhomogeneous. And you can also see that in general, the trabecular bone microarchitecture is reduced. So we have this trabecular thinning and also reduction in trabecular number in these patients. And interestingly, in type 2 diabetes patients, we find a very different bone phenotype. So here we have almost improved trabecular bone microarchitecture. However, we have this really severe increase in cortical porosity, which is really important for bone strength, since these cortical pores are discontinuities within the cortex where strains can accumulate, and from there failure can be initiated by kind of microcrack initiation and other bone failure mechanisms, which then lead to a subsequent failure of the entire system. And what's even more interesting is that we found that these alterations in bone structure were mostly present at the distal radius and were attenuated at the distal tibia, where we even found slightly improved bone structure in these diabetes patients. And this led us to believe that maybe the weight-bearing characteristic of the distal tibia, which is one of the weight-bearing sites and under constant load during day-to-day activity, may be somewhat protective or offset this negative effect of diabetes. So in order to investigate this further, we have to look at the bone remodeling process, because this bone microstructure is a result of this constant bone remodeling. And as you probably know, in this bone remodeling process, osteoclasts first resorb bone, then macrophages create an osteogenic environment, which is then new bone is laid down by osteoblasts, which is then further mineralized over the time. And in order to analyze this process, we of course have to basically monitor the bone microstructure over time in order to observe the changes, which then can be directly linked to the cellular behavior. So in this case, you can see if we take several HR-pQCT scans over time, we can link regions where bone has resorbed to osteoclast activity and regions where bone has formed, here in orange, to osteoblast activity. And even further, there's these osteocytes embedded in the bone matrix, which are believed to be the mechanosensors and kind of like orchestrate this entire process of bone formation and bone resorption. And in order to analyze their activity, we can link the local mechanical signal or environment to kind of like osteocyte function. And so all of these cells that I mentioned, osteoblasts, osteoclasts, osteocytes, and their progenitor cells are basically sensitive to mechanical stimuli in some form, but osteocytes are the main mechanosensors of the bone. So these osteocytes reside within the bone matrix in the lacunae, where it is believed that they can send several different mechanical signals, such as the fluid flow that induces shear stresses or the hydrostatic pressure. And then over their connected network, they can basically signal to the other bone cells in order to direct bone forming cells to regions where strains are high and bone resorbing cells to regions where it's safe to remove bone. So some indications of this kind of like load-driven bone remodeling process and dysfunctional adaptation of bone are, for example, that increased physical activity can lead to improved bone microstructure and bone strength. So here you can see a study where adult female recruits went through basic combat training, which is an 8-week program. And you can see on the left side an HR-pQCT scan before the combat training and on the right side after. And you can really see here in the bone structure how these trabeculae have thickened and overall BMD has increased. And when we now look at the other microstructure measurements, such as, for example, down here, trabecular thickness, trabecular separation, trabecular number, or cortical thickness, we can see that all of these have basically improved through the physical stimulus, or this like mechanical stimulus through the activity. And so this shows really nicely how mechanics can improve our bone health and how they can basically offset these negative effects of other diseases, as we've seen before in fracture subjects. All of these parameters were mostly reduced. Another really interesting study is this study that then looked at basically the loading dose that bone adaptation is related to. And they've had this really controlled experimental setup where they supplied a controlled mechanical stimulus with different high and low magnitudes or high and low loading rates, so different frequencies to the distal radius of participants. And they found that really high loading rates are really beneficial for bone adaptation and lead to better bone strength and kind of HR-pQCT measurements as well. An example for basically the opposite effect where unloading is experienced is, for example, in microgravity. And this is, of course, a very extreme case of astronauts that go to space, but it could also be associated with decrease in activity or even immobilization in some patients due to different chronic conditions or aging. And what you can see here is that basically once bone is unloaded, you really have a steep decline in your bone mineral density and also in your bone microstructure parameters. And it's kind of like acting with this like principle of use it or lose it. So if you don't use your bones, they will be resorbed and you will have a decline in bone strength as well. So this process there's very many indications that this process is regulated by mechanical stimuli. But of course, we want to investigate this also on a kind of like more local tissue level basis, where we can use finite element analysis to really analyze the local strain distribution. So how much bone is deformed in different regions. And we can then correlate this to our basically bone formation and resorption sites, which we identify with this time-lapse bone remodeling concept that I presented earlier from subsequent HR-pQCT images. And what we then can see there is that in regions of high mechanical strain, bone formation is more likely to occur. And in regions of low mechanical strain, bone resorption is more likely to occur. And this is, really good, because this basically means that bone is trying to adapt towards really high loads where there's like bone needed, it lays down new bone. And in regions where it's safe to remove bone and start remodeling, bone is being resorbed in order not to kind of like sacrifice the mechanical integrity during the bone remodeling process. And this way, the entire skeleton can be remodeled safely over time. And yeah, of course, these models are very sensitive and have been developed basically for mouse models before, and studied a lot in different applications, even fracture healing or defect healing with different loading regimes and so on. But these models come out of very controlled experimental conditions in these mouse models. And now studies are trying to kind of translate these models for a human application using HR-pQCT imaging. And two of the major challenges that I want to highlight today are first, the difference in loading conditions between these models, where in animals we have these experimental, highly controlled loading conditions, where sometimes even loading pins can be inserted to the vertebra in order to supply a very controlled stimulus. Whereas in human patients, it is much more difficult to control these conditions, especially at the radius where the wrist is used on a day-to-day basis for different activities. And this varies largely across participants or patients. And the other difference is that even though HR-pQCT is really promising with really good increases in resolution from like the previous versions and from QCT, it is still not at the level of micro-CT imaging, where micro-CT is really high resolution. As you can see here, we have a really crisp image of the bone surface, whereas in HR-pQCT, it's still fairly blurry compared to that. And so today, I want to kind of like highlight several strategies that studies have done in order to control for these problems, and then also highlight the studies that have used mechanoregulation and further show what indications we have in diabetes that there is a disturbed bone mechanoregulation in these patients. And so the first thing I mentioned, of course, is the resolution of HR-pQCT imaging that is lower, but that is actually not the biggest problem that studies have with HR-pQCT currently, because the newest scanner has actually 61 micrometer resolution, which seems to be sufficient for this bone mechanoregulation analysis. However, one big problem are patient movement and motion artifacts, because in mouse scanning or micro-CT, we can anesthetize animals and they are completely still during the scanning process, but of course we can't do this with patients. And basically the way an HR-pQCT scan works is that the scanner acquires projections over 180 degrees, which takes around 2 to 3 minutes per scan. And then these are reconstructed with a mathematical algorithm to reconstruct this bone microstructure in 3D. And this reconstruction method basically assumes that the object has been completely stationary during the scan. And you can think about this almost like when you take a photo with a long exposure and start moving your camera, or something is moving in your photo, then it will come out blurry. And the same basically happens here, where there will be a shift in the sinogram, and during reconstruction, the reconstructed image you can see here has these streaking and blurring artifacts. And it's really difficult to identify like a crisp bone microstructure, and therefore it's very difficult to track this microstructure over time consistently. And so what studies have done is basically they try to restrict patients, and there have been several rounds of improvements of these casts that are used for scanning. And here on the left side, you can see, I think, the current model that Scanco is distributing with the XHUM-CT2, which includes these inflation pads now, which weren't included in the previous generation, which basically fixate the patient with like some pressure even in order for them to not move. And there's even further developments where there's these finger and thumb fixations, because even slight movements of your hand or your fingers can basically, via the muscle contraction, cause motion artifacts in these images. And you can see down here studies that have performed bone mechanoregulation analysis. And what I really like to highlight sometimes is that when you look at the original cohorts and then the amount of subjects that were included in the final study, so the other ones were most likely excluded due to motion or other reasons maybe, but mostly they call out motion as the main problem. And these percentages are really, really low. So this makes it really hard to analyze mechanoregulation in large clinical cohorts because of these motion and blurring artifacts. So typically, motion is assessed on the scale between 1 and 5, where 1 means no visible motion artifacts and 5 means major horizontal streaks. And you can see the scale is fairly subjective. So it's very difficult for operators to basically choose a consistent grade. And that's why there's lots of disagreement between different operators, even after training. And so lots of studies have looked into assessing motion more quantitatively. One example is here with this study that tried to basically estimate rotations and translations within the sinogram based on differences between the first and last projection. And they've done this using this experimental setup and tried to quantify basically similar motion scores. However, these motion scores are not so intuitive as kind of like the scores between 1 and 5 that clinicians are used to. That's why, for example, we have developed a motion grading deep convolutional neural network that automatically scores images for patient motion. And you can see here basically how the neural network reacts to different images at different scores. And you can see that it's able to identify kind of like crisp bone microstructure and associate appropriate grades. And then for images that have motions, it really activates on these streaking and blurring artifacts, and then also assigns appropriate low motion grades, or like high motion grades, which is 4 and 5. And so, of course, it would be best if we could kind of just control better for motion or remove motion artifacts. But the current state is that this is really difficult. And we've tried this as well to kind of enhance images afterwards. But yeah, it's really challenging still. And so for that way, in order to get consistent image quality, is to control for only high quality scans to be included in your study. So there's at least no systematic bias within the data that you report. The second big issue that I want to talk about are loading conditions. As I mentioned, in animals, we have these really controlled loading conditions via, for example, loading pins, whereas in humans, there's different loading from day to day, and it's much more complex how, for example, the radius is loaded compared to the mouse caudal vertebra. And so I highlighted the study earlier already, where they tried to actually supply a very controlled mechanical stimulus to patients. And this is actually, I think, a really, really cool concept, where they have this radius loading device and then basically apply different magnitudes and frequencies to the distal radius of patients. However, the problem is that these patients, of course, also go home and follow their typical kind of like exercise program or not. And so there's still a lot of differences between the patients that you cannot fully account for with these controlled setups. So other studies have basically developed computational algorithms where you can, by computational modeling, identify somewhat of an estimate of how much loading the bone has experienced over time. And how they do this is basically they assume there's a limited amount of loading cases that the patient can experience. And then through optimization, they scale them together until they find a target tissue load, which they basically model as a homogeneous tissue loading, where they say that bone typically adapts towards the load. So this structure should be an adapted structure without any high strains or low strains. So then they scale these together, and they've shown that this actually works pretty well in animals, and they can pick up increases and decreases in loading in these animals. And so we went ahead and we further developed this algorithm because we said, okay, in longitudinal imaging, we actually have more information available now. We actually know that there should be higher strains in regions where bone has formed, and there should be lower strains in regions where bone has been resorbed. So we basically adapted the target stimulus that this optimizer uses, and then we have shown that this optimization outperforms the old algorithm in synthetic data, which is computer simulations, mouse data, where we picked up extra physiological loading and like one of these loaded animal groups. And then finally, we also correlated it to the grip strength in patients, where the muscle strength really is one of the major load components on the distal radius, and is therefore a good indicator of kind of like the activity or kind of like the loading that the radius experiences in a patient. Yeah, so this shows that basically it's important to kind of like estimate the mechanical environment appropriately in order to then correlate these two things, the basically bone remodeling with the mechanics, which is the mechanoregulation. And as I mentioned, only very few studies have done this yet. So there's 2 studies. This one was actually the first one that has shown in humans that there's somewhat of a form of load-driven bone remodeling. And as you can see here, what they've shown is basically that resorption sites that are detected with this longitudinal HR-pQCT are associated with lower strains, which they estimated by this load history load estimation algorithm, than the formation side. So formation had higher strains than resorption, which then led them to conclude that there's somewhat of this linear relationship between mechanical stimulus and bone remodeling. And there was one other study that followed up on this, basically this concept, and they've shown this similar kind of like trend where we have higher strains in formation and lower strains in resorption areas. However, they also found that the distance of formation areas is basically closer to high strains, but interestingly, also the distance of resorption areas is closer to high strains. And so they concluded that probably high strains initiate this whole remodeling cycle where first bone resorption precedes bone formation, which is why there's also a kind of like connection between these resorption areas with high strains. And of course, in diabetes, sadly, bone mechanoregulation, or fortunately, because that's basically what we are aiming at in the future, but it has not been investigated yet in patients. But there's some indications on cellular level, and I've already presented on the microstructural level, there's some indications where the negative effects of diabetes are attenuated at the tibia. But on cellular level, it is basically believed that this high extracellular glucose kind of modifies the matrix by increasing the thickness or including glycation end products, which then alters the fluid shear stress transmission mechanisms, which then results ultimately in lower calcium mobilization and lower ATP release. And this then ultimately leads again to a lesser activation of these mechanosignaling molecules, and then ultimately to a lower response of the diabetic bone cells to mechanical loading. And because of these cellular studies and other indications on the bone microstructure level, we believe that this mechanoregulation analysis would be really interesting in diabetic patients, and this is what we're aiming for in the future. However, there's still limitations of this analysis. So basically, bone mechanoregulation, or somewhat of a load-driven bone remodeling, has been shown in humans. However, there are not really very many quantitative markers yet, and the reproducibility of these methods has also not been validated. And in order to compare basically mechanoregulation in diabetes patients with mechanoregulation in controls, we need these robust subject-specific measures that basically quantify somewhat this mechanoregulation in patients. And what we're currently developing is a resorption, or a load-driven resorption and a load-driven formation measure in forms of odds ratios that describe basically the likelihood of bone to be resorbed with decreasing strain, or the likelihood of bone being formed with increasing strain, and an overall measure, which is this correct classification rate, which basically says how well is the mechanical signal overall correlated with the bone formation and resorption sites. And in this study, we're currently trying to validate with scan-rescan pairs if we can reassess mechanoregulation in individual patients and to what degree, and then basically classify kind of like the precision of these methods. And so once this is done, and we're hoping that we can analyze bone mechanoregulation in diabetes patients. But for today, I want to finish here because this is all very current developments. But in summary for this webinar, I want you to take home that mechanical stimuli are really essential for skeletal health, and that patient motion is still one of the biggest challenges in HR-pQCT imaging, not only for mechanoregulation, but also for all other microstructural measurements. And therefore, these automatic scoring methods are really important to basically create consistent measures. And then for mechanoregulation, the loading conditions are very important, especially at sites like the distal radius, where there's very different mechanical environments from patient to patient. And finally, mechanoregulation has been shown in humans, but the studies are very, very limited, and there's no really very many quantitative or reproducible measures yet that have been kind of like assessed in these patients. And then finally, for the diabetic bone mechanoregulation, there are indications that there's disturbed mechanoregulation in patients with diabetes. However, it has not been shown in vivo with these imaging methods yet. But we're hoping that we can do this until the end of the FIDELIO project. So I would like to thank people that have contributed to some of the results that I presented here and some of the studies, and of course the FIDELIO Consortium for letting me present here today.